Okay, so with what we did yesterday, you now have actually one complete tool in your toolbox for this course, which is how we do system analysis, how we describe a system, how we describe a signal, and how we take those two descriptions, put them together, and use them together in order to determine what's going to come out of the system for a particular input signal and a particular set of initial conditions. So what we have so far for how we would describe a system is through a differential equation. And that was, in essence, an input-output relationship that related the output, the y of t for the system, to the input x of t and its derivatives. And if we wanted to do system analysis using a differential equation, you had to give me that differential equation, give me a set of initial conditions, give me an input signal, and I would solve this differential equation for that particular input and that particular set of initial conditions, and I could tell you what comes out of the system then. So we have a description and a system analysis method, differential equation and solution of differential equation. Where we're heading next is another method for doing that same thing, for solving the system analysis problem using a different kind of description of the system, a different kind of input-output relationship, and a different method than solving the differential equation. Now it's going to be a method that's kind of tied back to this differential equation solution, but it's a whole new way of solving the problem, still in the time domain, still in normal signals kind of land, not using any kind of mathematical transformations, but just using the properties of linearity and time invariance to solve the system analysis problem. So now I'm going to use for my description of my system not a differential equation, but some kind of system response function, meaning a special function, I'll call it h of t, that's nothing more than the output y of t when x of t, the input, is some simple input function. Now, the trick is choosing x of t very cleverly so that the output of the system for this simple input function is something that I can generalize, something that I can use as the basis for figuring out what is the response of the system to any signal. And the key will be choosing a simple function that is the right shape so that I could express any input function in terms of a collection of those simple functions. Because then I can use superposition and time invariance to directly compute the output of the system in the same way we've been doing it by onesie-twosie kind of examples so far. So our next goal is to come up with a useful way to characterize the response of a linear time invariant system using some kind of simple input function. And we want this method to give us a lot of information about how the system's going to behave with any other input signal. So I've got to be careful about my choice of simple input functions, one that can generalize. And being engineers, we want to get as much information as possible with as little work as possible, because that's how we roll. And it would be nice if I chose a simple signal that was one that I could actually create in the laboratory. So you give me an unknown circuit, I could apply this test signal, measure the response, and from that infer what is the response of the system to other kinds of inputs. So that's what we'd like to do, and that's what we're going to try to do today, try to accomplish all of that. The idea being that if I've cleverly chosen my input signal, and I know the response of the system to that simple signal, I know if I put in a delayed version of that input signal, I'll get nothing more than a delayed version of the known response. And superposition says if I can scale and add combinations of those simple signals, that the output can be determined directly through superposition. That's actually what we're going to be doing today. And because derivatives and integrals are also linear operations, if I know the response of the system to some simple function, I know the response of the system to its derivative or to its integral. I just take that same response and integrate it or differentiate it, whichever operation I did to the input. So I'm going to push this superposition for all it's worth. Okay. So if I, excuse me, put in an input, a signal to a system, put in an x of t, out comes y of t, and I know y of t is always made up of two pieces, a forced response and a natural response, right? Or if you prefer, zero input response, zero state response, but let's use these combinations. So if I input a signal to a circuit and measure its response on the output, that response will have both of these pieces. Which one tells me about the internal makeup of the circuit or the system, its internal dynamics, its R's, L's, and C's? Is it the forced response that gives me that, or the natural response? It's natural response. So I'd like a input signal that's going to let me see that natural response and maybe recognize it as easily as possible. Okay? So we do want to see the natural response of the system, because that does tell us what's going on inside the circuit. It's the left-hand side of the differential equation and the characteristic equation, the y of t and its derivatives, that tell me about the internal makeup of the system. Okay, and if I input a signal, I'm going to get the total response. The natural response is going to be the piece that I'm going to see as a transient response. And so that's going to be my way of picking it out. Now, I have no choice. I have to input some kind of input signal. I have to stimulate the system to get a response. And so I'm always going to get a forced response, because I always have to force it with something to see it do anything. Right? I'd rather not. I'd rather just see the natural response. But, okay, if I've got to force it with something, and that forcing function input's going to create a forced response, let me be careful about the one that I choose. Let me choose one, before we do that, that's easy for me to spot. Let me choose a x of t that creates a forced response that I could easily recognize, that I could spot right away, and even better yet, that I could easily subtract out, back out of the total response to leave me just the natural response. Okay? Any ideas of a good function that has a easy to pull out shape? What kind? A constant? A DC value? Starting at time t equals 0, so a step. So a constant or a step function would make a good choice, because if I put a step function in, what's the forced response going to be? Say it louder. Also a step. Also going to be a step function. The forced response generally is going to have the same shape as the forcing function, just going to have some unknown constant, some unknown size, right? But if you give me you put in a step, and my system does that, well, I'll just look at where does it settle out at, and I'll call that piece the forced response. That makes all this wiggly stuff the natural response. Okay? So using a step, a constant step, gives me an easy to recognize, easy to remove forced response. Agree? Okay, that's our strategy. Now, the other thing I'm going to do is say, let's keep it simple by, let me make sure my system is completely relaxed, completely discharged. All capacitors are discharged, all inductors are dead, or if I've got springs and dampers or other things, all the initial conditions are 0. Otherwise, I'll have a 0 input response. It's still doing some transient stuff based on old inputs. Let me just get rid of that. So we'll start with a relaxed system. Okay. And you already told me this. What input signal makes good sense to meet all these criteria, and a step is a good one. It's easy to recognize, it's easy to extract, and we can create it in the lab. So check, check, check. Does all the things I wanted to do. All right. So we'll put in a unit step, and we'll measure what comes out. And whatever comes out, we'll call S of t the unit step response. All right. Now, again, let's not lose the forest for the trees. Why am I doing this? Well, if I know the response of the system to a unit step, if you gave me some other input, x1 of t versus t, can't draw a straight line, and that input looks like, I don't know, a bunch of steps. Then if I know the response of the system to one step of a height 1, I know the response of the system to a step of height 4, or a delayed step of height 2, or a downward step of a certain height. I can use superposition on this response and add them up to get the response of the system to a more complicated signal. So that's what we're aiming at. Okay. If we were doing this in a lab, tell me, how would you measure the step response of a circuit? Literally, how do we do that? So you've got an RC circuit. We're going to use a simple low-pass filter RC combination, series combination as our test circuit today, because it's easy to analyze and we'll be able to put all the pieces together on it, and it's a response we'll use all of our techniques on. So you have an RC circuit, you wired it up in the lab. How are you to measure the step response? What are you going to connect to the output to observe the output? Put an oscilloscope on the output. And what are you going to connect to the input of the circuit? Function generator, okay? So we hook up a function generator, and what are we going to set the function generator for? Square wave. So the input, x of t, is going to be some kind of square wave. All right. Anything I want to do special to the parameters of this square wave to make it really good for a step response? Lower the frequency. I want low frequency. What's that going to do to my waveform? Spread it way out. Use a really low frequency. How else might I even extend it even more? Make it DC? Well, I want a step. I need a step to initiate it. What's the other knob I can affect on a rectangle wave? Duty cycle. Set the duty cycle some high percent, like 80% or 75%. Then my square wave lasts, my on time lasts a really long time. So the problem you're working against, if the circuit reacts quickly, right? You want it to be settled out before your signal goes away. If it's really slow responding, it's not done by the time this goes away, well, you're going to get a false measurement. Right? So we want to make sure we're on long enough to let the circuit response finish dying out with that on time before we take the signal away. Okay, let's do that. So here's a simple RC circuit. We wanted a relaxed circuit, which means the voltage across this capacitor is the only thing that can have initial conditions. We'll say that equals 0, so it's discharged at time t equals 0. We'll hook up a function generator to the input, set it for a rectangle wave, high duty cycle, low frequency. So it's giving us a pretty constant input. And hook up a scope, see what comes out. We're on your extra supplement page here. So we put in the step and we get this shape out. Okay. Let's zoom in on that shape. Look at the scope screen here. I put in that, a unit step, and I got that on the output. All right. What's the forced response of that in that output? U of t, we said it would have a unit step shape, and what's the height? 1. It settles off to 1. So we know the forced response after the transients died out The forced response is holding it up, and that's got a height of 1. All right? So we know that. How about the natural response? What shape is that? What kind of mathematical function does that natural remaining part look like? Exponential. And is exponential one of my choices for natural responses? Yes, it is. So it's got some exponential response. Some unknown k e to the alpha t. I don't know what alpha is. I don't know what k is yet. Can I get those from this wave shape? Yes, right? So every point on that curve has to satisfy this relationship. It's a forced response plus a natural response. Forced response we know is 1 u of t. The natural response is some unknown k e to the minus alpha, or e to the alpha t, u of t. So plug in any value of t for time, find that point on the curve, and that voltage should gives me the left-hand side. We'll plug in that value of t for the right-hand side, and we can solve. Well, I'm going to need a couple points to solve for my two unknown coefficients, the k and the alpha. I need at least two equations. Let's do that. Let's solve for k first. That's easy. My favorite position would be let t equals 0 just after 0. So I'm just after the input has happened. Just after the input has happened. The output is still 0. And time is 0. So if we plug in t equals just after 0 into this equation, the u of t is a 1. This u of t is a 1. This t is pretty much 0. So I have a 1 plus k e to the alpha 0, which is the same as 1 plus k. That equals the height, which is 0. So k must be minus 1. Could I have inferred that k had to be negative? This exponential had to have a negative coefficient in front of it from that shape? What if it was positive? What would have my total response would have been a step plus a positive exponential, or with a positive coefficient in front of the exponential. So it would have been something like that as a total response. Right? With the negative k, I got that shaped response. Okay, so far I'm liking my answer. It's matching up with what I've got here. So we know k is minus 1. Now I want to solve for alpha. Let me plug in either of these 2 points for y of t and solve for alpha. So if any point is 1 minus 1 e to the, well, that should be plus alpha t, sorry. Then plug in the voltage at this point and the time at that point, or the voltage at this point and the time at that point for the voltage and the time. We can rearrange this equation. We can exchange these positions. We can take a logarithm to get rid of the exponential, divide by t, and we can have an equation for alpha in terms of the voltage and the time of any point on that curve. So we'll plug in this point here. At time t equals 6 seconds, the voltage is at 0.95 volts, and solve for alpha, and we get minus 1/2. So now I know the total step response of the system is a 1 u of t minus 1 e to the minus 1/2, or 0.5 t u of t, or if you prefer, 1 u of t minus 1 e to the minus t over 2 u of t. Okay. So we got that from measuring the output of the system. Now, I cheated a little bit. I looked at this exponential, and it was a gamble that this shape was just one exponential. There could have been two in there with different time constants. It could be a combination. So far, it looks like, and if I plug in different values on here, it does satisfy this equation, so I think I'm okay with a single exponential. But strictly speaking, that was a supposition. I couldn't have necessarily seen that directly from the response, other than it looks like a simple exponential. So we could start with that model. Okay. Everybody okay with how we got that? All right. Now we've lost the forest for the trees. Why are we doing this again? What's the point? I know the response for a step. Now, if you give me an input that's a collection of steps, I can tell you what the output's going to be. It's going to be a bunch of combinations of these. Okay. Oh, sidebar. Can I tell some of the differential equation of this system from that result? I know the forced and natural responses of the system. Well, actually, I can plug in my values here now. Forced response, this was a -1 for K. This was a T over 2, or 1/2 for alpha. There's a negative out in front. Oh, by the way, how did I know alpha? Should I have been able to infer that alpha was negative, not positive? What told me that from that shape? It's bounded. It's dying off to a level. It's settling down, so I needed a converging dying off function. So I needed an exponential with a negative exponent. So, okay, I'm liking the answer I got. This is the response of the system to a unit step input. Can you tell me what are the roots of the characteristic equation of this system? We're going to put the pieces all together here. Where am I going to find the roots of the characteristic equation? In the exponent of the natural response. So this has a root of the characteristic equation of s equals -1/2, right? Which would give me this term in the natural response. So that means my characteristic equation must have an must be s plus 1/2. I only have one term in the natural response, so I must only have one root of the characteristic equation. I must have a first order system with that one root. If this is the characteristic equation of the system, what's the differential equation of the system? At least the left-hand side of it. Y prime of t plus 1/2 y of t equals, I don't know. I don't know if I have x of t, I don't know if I have x prime of t. I can't necessarily infer what's on this side, but look, I've got the whole left-hand side of the differential equation just from measuring its response. Not bad. Pretty good. Okay. That's how we would do it in the laboratory. What if we wanted to do it analytically? Can we determine the unit step response analytically and relate it to the circuit element values? If we knew the differential equation that describes the system response. Can you do that? Answer is absolutely. The answer is, I can do that, Professor. It's no problema. I've been doing it for homework. I've been doing it on quizzes. I can handle special cases. It's easy. Well, I can do it. It ain't easy, but I can do it. It takes a lot of time. It takes a lot of work, but I can do it. Let's do it. All right. I need a differential equation for this circuit. I'm going to put x of t is going to be my input voltage. Y of t is going to be my output voltage. I'm going to start with the system relaxed, which means the capacitor initial voltage is 0 at time t equals 0. I'm putting in a unit step. I want to know what comes out. Let's solve that differential equation. What is the differential equation of this circuit? Does anybody see any differential equations up there? I see no d by dt's up there. I see no primes up there. I got nowhere to start. I need a differential equation. Where am I going to get a differential equation? I need some derivatives. Give me some derivatives. I need derivatives. Is there a derivative up there? Voltage. What voltage? Capacitor voltage. Capacitor voltage? Give me an equation. C dV dt. What is C dV dt? That's the current through the capacitor. The C dV dt in my circuit, which V is it? The capacitor voltage, which is also the output voltage. dV out dt is the capacitor voltage. Okay? I like it. I got a derivative. I don't see any input voltages up there. I don't have an output versus input thing going on here. Can you give me another equation for the current through the capacitor? IR. Well, I is V over R for the resistor. And what's the voltage across the resistor in terms of my V out and V in? Say again? V in minus V out. Everybody okay with that? The voltage change from here to there is V in minus V out, and the current is that voltage divided by R. Voila! I have a differential equation. I got derivatives, I got V out, I got V out, I got V in, I got circuit elements. I'm happy. Yes, circuit analysis. There's a reason we taught you that stuff in 112, 211, 212. Now, we're going to take the differential equation. We're going to input a unit step and figure out what is the step response. And so, yes, that's the differential equation we're looking for. Now, in our normal form, we would have put all the output terms on one side. So I'm going to put my V outs or V capacitors on one side, V in on the other side. So I have my Y of t's and my X of t's. And in our standard form, the highest derivative of the Y of t, we like a leading coefficient of 1. So let me divide everything by C. And then here is the circuit differential equation. If I want to cast it in terms of my system variables like X and Y, I'd replace VC with Y, V in with X, and let's not keep writing RC. Let me replace that with tau. But you knew I was going to do that. Tau is the time constant of that circuit. And we'd have this as our differential equation. Y prime with t, first derivative of the output, plus 1 over tau, 1 over RC, times the output, VC, is 1 over tau, or 1 over RC, of the input, the in. First order linear constant coefficient differential equation. Now when I ask you, can you solve that differential equation? You say, absolutely. For a relaxed system with a unit step input, let's do it. We only got 20 minutes left. Can we do it in 5? What's the zero input response of that system? 0, because it's relaxed. All relaxed systems have no initial conditions, no initial condition response. It is relaxed. So I don't have to worry about that. Okay, zero state response. First we need a, oh, wait, this is a general differential equation. Even though I'm just dividing the input by x by tau, I have to treat that like a general case, which means I have to solve the single input case first and then generalize it. So let's do that. There's the single input case. We just have x of t on the one side. Forced response for a unit step is unit step, or in terms of t greater than 0, my input is a constant, so my output response is a constant as well. We're going to plug in the constant into that differential equation. For the actual input, where the input at time t greater than 0 is 1, and have first derivative of the constant is 0, 1 over tau times the constant equals 1, so c must be tau. Handy. Right. If any of this doesn't make sense, so this should be mostly review at this point, but if anything's not clicking, now's the time to ask. Okay. The rest of the zero state response is the natural response piece. For that I need the characteristic equation. What's the characteristic equation? S plus 1 over tau equals 0, so S must be minus 1 over tau, which means we have a natural response piece that's ke to minus t over tau. Add that to the forced response, which we found was just tau, plus ke to minus t over tau. Use the initial condition, the zero state response at time t equals 0, first order system, one initial condition, equals 0 for zero state response. I get tau plus ke to the 0, which is just tau plus k, equals 0, so k must be minus tau. Making the total zero state response for the single input case, the forced response tau, minus tau e to the minus t over tau, and I put a u of t around the whole thing. Now if we generalize that for this equation, what do I do to this single input case zero state response to get the zero state response of the general system? Just divide by tau. So we'll take our zero state response for the single input case, divide it by tau. We get u of t minus 1 e to the minus t over tau u of t. I have no zero input response, so that's the whole answer. That is the step response, 1 times u of t minus e to the minus t over tau u of t, and we erased it. But that should agree with what we came up with when we measured. By the way, what was tau for our circuit that we measured with the oscilloscope? What was the numeric value for tau? 2. We had a e to the minus t over 2, or e to the minus 1/2 t. So tau was 2 for our circuit that we measured with the oscilloscope. Here it is in general. All right. So that looks like that same shape we got. What its actual, how fast it rises, how fast it reaches the final value depends on the time constant, the tau value, the RC. So if the combination, the product of R and C was 0.01, then it's a very fast exponential decay. If tau is 0.5, you get this much slower one. Now our tau was 2, so it's even slower than that. Took it out to about 10 seconds to settle out. Okay? So this is the general solution for the response for any circuit. You put any value of R and C in there and you can get the step response of the circuit. Oh, by the way, if you had actually measured this, the other way you could infer tau or pull out some important characteristics of these shapes. 2 characteristics we usually measure in the lab. One is called the delay time, at T sub d. That's how long does it take you for your output to go from where it starts to where it's going to end up. How long is it going to take it to get halfway there? So in this case, because I'm starting at 0, ending at 1, I find a height of 1/2, see what time that happens on the green curve. It would be at this point, and call that the delay time. Since we know this expression should identify every point on the curve, we can solve this equation for t delay by setting this equal to 1/2. So we said 1/2 equals 1 minus e to the minus t delay over tau. And if you go through the mathematics, you find out that the time constant of the circuit is related to the delay time by about a factor of 0.7. The longer the time constant, the longer the delay time. That makes sense. Now that's probably not the one you measured. If you measured these in the lab before, you probably measured the rise and fall time of the circuit, right? And by that, we usually talk about the 10 to 90%. How long does it take you to get from 10% to where you're going to 90% of where you're going? What's that difference in time? And again, we can use 2 points on this equation, 2 voltages, 2 different times, solve that through the exponential using the natural log, and find that the 10 to 90 time would be about 2.2 times tau. So you measure the rise time, you can also infer tau. If you measure the delay time, you can infer tau, or you can do it by single points as we did it. Okay, that's sidebar. Meanwhile, back at system analysis, here we go. We have the step response of the system to unit input. What would be the response of the system to this input? It's like 2u of t plus another u of t minus 2. What's the response of the system in terms of s of t's? Right. If u of t gave me s of t, 2u of t's gives me 2s of t's. And the delayed unit step gives me a delayed step response. So the total response would be 2 of these plus 1 of these with t replaced with t minus 2. That's using linearity and time invariance, superposition, to infer the output using a known input. That's the method we want to generalize today. That's when we want to push that to the max. Does everybody understand what we're doing there and why we're doing each of those, how that works? That's linearity and time invariance restated. This is because of linearity. I can scale. This time shift on the input is the same time shift on the output. That's time invariance. The fact that I can add inputs gives me added responses. That was additivity of linearity. It's all those properties together we're taking advantage of here. Okay. So you give me any input that looks like a bunch of steps and delayed steps and scaled steps. I can tell you exactly, I can give you an analytical answer for the output of the system, just as we did there. Just taking it a step further. Okay? That's pretty good. That's not quite good enough, but that's pretty good. Why do I say it's not quite good enough? Well, that's fine for any signal that looks like this, but most of my signals don't look like that. They're not steppy, blocky. You know, I want to put in exponentials. I want to put in sines and cosines. That's maybe not the best choice. It's an easy choice, and it's a great one for accomplishing what we want. We're on the right track, but we got to push this a little further. Before we push, are we okay with the setup? Okay. Found the step response, so we can generalize that to the response to any other collection of steps. We did it by measurement. We did it by analysis. All right, here we go. That brings us to impulse responses and convolution, the bane of EE228 students. It looks like mathematical gobbledygook. It makes no sense at all until suddenly the light goes off and the mathematics fall away, and it actually is a very simple concept. It's really just what we just did, superposition, applied to a very cleverly chosen simple input signal. We're going to apply linearity and time invariance to a cool response, to a cool signal, and get the answer for any arbitrary input signal. Here's the way it works. Okay, again, you give me a signal that you know the response of the system to, If we scale and shift that input, we get a equally scaled, equally shifted response. That's linearity and time invariance again. So that if we make a collection of these scaled and shifted weird functions, the response is a bunch of scaled and shifted weird responses. Okay. So I want to choose an input signal, a simple signal, that's really good at becoming a model for any input signal. Whatever that is, we'll call it some simple function as f of t. If I can have a way to mathematically figure out what's the response of the system to that simple function, we'll call it a simple function response, then if I put in a delayed version of the simple function, I get a delayed simple function response. If I get a scaled one, I scale it. And so I want to be able to model any signal, any shaped input signal, as a collection of scaled and shifted simple functions, just as we did with the steps. I want to be able to do that to any signal. So a step isn't so good. It goes on forever. But even think about, even as it's shown, a rectangle. I could kind of make a approximation of shapes with a collection of rectangles. So if I knew the response of the system to one rectangle at time t equals 0, I could know the output of the system to a bunch of scaled and shifted rectangles. It's just a bunch of equally scaled, equally shifted rectangle responses. Superposition says that, linearity and time invariance. Okay, let's do that. Let's do it exactly like I just said. Let's approximate an arbitrary input signal, x of t. Can have any continuous shape we want. I'm going to approximate it with a bunch of rectangles. A bunch of rectangles with a width of delta t, whatever delta t is. So that's a rect of t over delta t, right? And I'm going to be able to make a bunch of those. I'll start one centered on t equals 0. I'll butt them up right next to each other so that the centers of each one, well, they have a width of delta t, so the centers are spaced by delta t. So this one's centered on 0, this one's centered on delta t, 2 delta t, 3 delta t, 4 delta t. Anyone in general is centered on k delta t. So this red rectangle function is just an example of one of them. Would be a rectangle of a width delta t shifted by k times delta t. So are you okay with this rectangle function here in red describing this red rectangle? All right. The other thing I'm going to do is scale the height. I'm going to scale the height of each one to match the intersection of the rectangle center with that function. So that those center points give me the approximation I want for the function. So this point is at x of 0, this is at x of delta t, 2 delta t, 3 delta t, on and on. So this rectangle is that rectangle shifted rectangle function multiplied by the original function x of t evaluated at its center point, k delta t. Are we still okay with the math? So I'm saying this rectangle of height delta t, positioned where it is, that this height is described by this function, where x of t is my original function I'm trying to approximate, and the rest is as it's stated. Okay? Anything there that's, I don't like it? Okay. Now the magic begins. Oh, well, I'm going to need a whole bunch of them, right? If this function x of t goes off infinitely long in both directions, I'm going to need k to have values 0, 1, 2, 3, 4, 5, all the way up to infinity, and all the way back to minus infinity. So I'm going to need to sum up a bunch of rectangles from k equals minus infinity to plus infinity. And I'll have not my original signal, but a kind of staircase approximation for it. Right? All right. I don't like staircase approximations. We want to make it better and better and better and better. How do I make that better and better? Well, you know the story. We're going to put the rectangle in, get a rectangle response function. Shifted gives me shifted, scaled gives me scaled. And so we're going to add up all these rectangle functions so that the response, the output, is just a bunch of equally scaled, equally shifted rectangle response functions. Right? That's linearity and superposition. Okay? How do I make that better? How do I make my blocky approximation closer and closer and closer to the original signal? Let what parameter go where? Delta t go to 0. Make the narrower and narrower and narrower and narrower. So let delta t go to 0. We get more of them, more of them, more of them, more of them, better and better and better, till we get better approximations of our original signal. Okay, let's do it mathematically in 4 minutes or less. Remember, we had this model for an impulse. It was a rectangle with width delta t and height 1 over delta t, right? And we let delta t go to 0. That made an impulse. It got infinitely narrow, infinitely tall. All right. I've got something similar here. I'm letting this rectangle function, well, it's a shifted version, but it's still a width delta t. It's not scaled by 1 over delta t, but I still want to let delta t go to 0. Well, I'll contend that the limit of that rectangle, that shifted rectangle, as delta t goes to infinity, is a shifted delta. But since the delta has a 1 over delta t in front, I need to put that back here. So are you okay? So I just basically took this equation, multiplied it by delta t, and got this one. So this, and said, well, if I shift the rectangle, then the delta also shifted to the same center position. All right, now the magic. So I'm now expressing my input as the limit as delta t goes to 0 of a collection of shifted delta functions multiplied by x evaluated at this where the delta function fires and multiplied by delta t. All right. Now, I've got a summation. In the limit, those deltas start bumping up against each other. And, okay, well, repeat the story one more time. Here's what I'm doing, and here's ultimately where we're going to end up. I want to put in a delta function. I don't know how to do that, but if I could put a delta function into the system, what comes out I'll call the impulse response. And it's so important I'll give it its own letter. We'll call it h of t. Then if you give me a bunch x of t expressed as a collection of scaled and shifted impulses, then the output is similarly a collection of scaled and shifted impulse responses. That was the restatement, yet again, of linearity. There's the bell. Let's get to the punchline. Here's the last mathematical trick. As delta t goes to 0, delta t becomes a differential d tau. That goes to 0. This limit of a sum times delta t goes to an integral d tau. The summation becomes an integral, becomes a continuous function. This spacing between delta functions, k delta t, becomes a continuous variable, call it tau or lambda. And the input then, re-expressed as a continuous integral, becomes x of tau. K delta t became tau. K delta t became tau. A sum, an integral, of shifted impulses multiplied by x at the center of the impulse. And the response became an integral of same scaling impulse responses with the same shifts as on the input. This is what we came for. This is the convolution integral. This is the one that if I just threw this at you, you would say, what do I do with that? But now you know how to read that. It's just linearity. If the input is a sum of scaled delta functions, the output is a bunch of scaled, shifted delta function responses. Done. That's convolution, and tomorrow we'll see how to find the impulse response and how to solve a convolution integral. See you tomorrow.